在录制此会议。
Okay, welcome. So here's what we want to say is that how much charge accumulates along the surface with different condition related to the volume. So maybe we give a more general introduction that what is the action. So if you draw this image, maybe we draw it like a three-dimensional case. Okay. Here is before we apply additional voltage. It is a dielectric oxide. Maybe I don't say the oxide first. We call it oxide layer, silicon oxide. And what is the relationship between the silicon oxide? Here is the charge from metal. So we can think here so we have a thin metal layer, and we get a positive charge along the metal. Here is metal. And then the thickness of this oxide is P oxide. Thickness of this oxide. And what we define is here is the dimension W. Define what is the corresponding maybe width of this metal plate. And here is the channel length as we mentioned. And we try to separate the individual parts, like here is the BQ. And here will be BQ here because it's in semiconductor part. Okay. So what is the corresponding capacitance? So you can think the capacitance induced by this area. This area, the capacitance will be C epsilon outside over the area. What is the area? You can consider the area will be this sheet, right? Because it is a dielectric plate. And what is the area of this sheet? It is like is dx. Here is the dx multiplied with w. Okay, so you can see the total epsilon or the unit epsilon w dx. And what is the distance between the capacitance between two plates? Is P oxide. So you can write this area or the unit capacitance like this way. What is the area of the charge separation? And what is the distance between these two charge separation? We get the epsilon outside W dx over P outside. Okay. And typically, you can say it is like a strip capacitance. And then for this strip, you can try to get some simplification. So what I don't want to have is okay. So this epsilon P oxide is like a unit capacitance without considering the unit area. So you can write this as C oxide W dx. Okay. So the C oxide means the epsilon x over P oxide. It is what we have there. So if you consider this way, this one it is what we have, the C strip, the capacitance along this strip. And then that means if you get this capacitance along this strip multiplied with the voltage difference, you get how much local unit charge along this section or along this strip. Okay. And then typically is the epsilon oxide. If you are interested about it, it will be 3.9 multiplied with epsilon naught. What is epsilon naught? 8.85 times 10 to minus 12 as a coefficient. Okay, so if you are interested, you can also write 3.4 multiplied with 3 10 to minus 11. If I'm not correct, if I'm not wrong. N over n squared. N not squared. Maybe you can check. I'm not sure if I have the right wrong typing here. And then the regular T oxide is around 10 nanometer. Below 10 nanometer below. But I think this outside is thinner and thinner because they want to not actually thinner actually. So you can use the thick one by replacing it with different material. But if you are working with outside, the thinner one could be just 10 nanometer because we want to avoid any leakage current between the outside layer. Okay, so we previously mentioned, I think if you want to have a perfect boundary between two conducting material, the safe bound will be 10 nanometers. That is what happens the same with the L gate. Yeah. The gate distance is distant 10 nanometers. There will be some leakage in between. Okay. So when you come with this strip that we multiply with the voltage across VGS minus Vx minus Vd, if this Vx is the drain is not connected with positive voltage, you can get rid of Vx. It will go back to Vgs over minus Vt. It is exactly the same with what we have for metal oxide semiconductor. That's weak. Okay. And for this one, we can try to evaluate what is the charge and what is the total error. But let me talk more away. So here is source side, here is the drain side. So if you want to see what is the corresponding voltage, so you can see here is the 0 volt, here is the VS. So you apply the VDS along the drain to both sides. And here VDS, you can say any point in between, like the corresponding condition. Here we label 0 to X, here to X. And here is the voltage at X point. Okay, so that means you get a linear interpolation of interpolation of voltage difference between source to drain. And that assumes we have a uniform doping of this semiconductor. Okay, so there's no defect, it is an ideal case. And once you have this one, you can say here is the if you apply the positive voltage, what is the direction of your current? The action of your current will flow into the drain to the source side. So the current direction will be ID along drain to source side. And what is the electric field? So if you consider the electric field, it will be the same position. Here is the electric field. And then the electric field will be proportional to what? Electric field multiplied with distance equals to the potential difference, right? So if you want to look at what is the electric field, you take the difference in potential divided by the distance. So this electric field equals to Vx over dx. Okay, dvx over dx. So you can consider the electric field at each point can get a difference in between the voltage and the distance along x. So for this one, you consider what is the current. So for this one, it should be trip current or diffusion current. Let me remind you for BJT, what is the current we have? We consider diffusion current. Because the voltage we apply to induce additional multi-carrier, we get a carrier distribution. And why there's no trip current? Because for the depletion region, the majority carrier is recombined. There's no majority carrier. So we only consider the diffusion current of multi-carrier. That is for BJT. But for most data we discussed here, we build up a channel, which is the multi-carrier. And this channel will be proportional to what voltage we apply. And for this constant, we have an electric field building, this one. And this means we get the carrier freely movable inside this channel, proportional to the electric field we apply. Okay, so it is shift current. Does anyone confused about what is shift current or diffusion current? Diffusion current means that you have a carrier concentration difference. So it will move the carrier from high concentration to low concentration. Shift current means you have a built-up electric field in between the material. the electron or hole will follow the electron field, move away, move around. Okay, so for this one, we talk about the drift current, which is proportional to Q N mu N E. Okay, because we know the carrier we conducting here is the electron, so we consider the mobility of the electron, the number of electron, and the Q multiplied with the electric field. Okay, and so we say the electric field will be multiplied with mu E to be the velocity of your carrier, right? Your mobility multiplied with the electric field means the velocity. So velocity multiplied with the number of carrier multiplied with Q means the current. Okay, just to remind you what we previously did. Okay. And sometimes if you look about in the textbook, usually you may get a negative sign here because we define the x from 0 to x. So the electric field is this way, and they typically have a negative sign. Right? Because you take the voltage difference, it will give you a negative. This one will be a positive slope because you have voltage increase versus x. But your electric field is actually on the inverse way. Okay, just to make sure you know it. So for this one, you get the I, the charge. You can see what is the ID. Okay, so the ID, maybe I start from here, equals to, depending on how do you define your I. So for instance, if you define your I based on this equation, maybe we just start from ID. So you get the mu N Q. Okay, apply with E. But this one, we know the current is in negative direction. So depends on if you want to add a negative sign, but you know the direction, right? So it is fine if you didn't want to add additional sign. And what is N? N is the charge, right? The charge accumulations along this channel. So you can say this I will also be proportional to dq dt. Okay, so how much charge difference or regulation within time? And then once we get the increasement of the charge, that means the charge will be supplied by the external current. If you get a decreasement of this charge, that means your current will flow out from this point. Okay, so the charge difference versus time within this position. And then this one can be rewritten as dq dx dx dt. Okay, so you just cancel out and get it back to the same form. And what's the dx dt? This one is actually the velocity, right? The charge movement. And the dq over dx, that will give you back to this term. So you can say here's the dq, here's the dx. So you can rewrite this one dq dx equals to minus d outside w vg x minus vx minus vt. Okay, so you can put everything back to the equation. So what we eventually get is mu n c outside, and here's the mu n or mu vg x minus vx minus vt, and there's no mu n here because we start with this equation. So c outside w vgs minus vx vt is the dx. Here is the velocity. So we get a mu n multiplied with e. And then so we try to replace this electric field. So what is this electric field? This electric field equals to dV dx. So we want to replace the voltage here. So you get the dVx dx. So eventually, because the directions will be negative, so you get a negative sign in front of it. So you get a negative sign, mu n. You take the mu n out of bracket. The outside W VGS minus Vx minus Vt. Apply with the Vx. Okay. So this one, do not confuse about the Vx. Vx here means the voltage versus x. This one. Instead of confusing it with the velocity, sometimes people use the velocity, like a small letter v, to describe the velocity, but here's this potential. Okay, so you can see it is like a point in from drain to source with the mu n c outside w VGS VGS minus Vx minus Vt dVx. So that will be similar to this one. Okay, you can check about the sign. I didn't carefully have the negative or positive sign here, but you can see eventually you get the ID point out in from drain to source. And for the electric field, we proportional it to the minus potential over the x. Okay. So what happened here is that we just locally consider the charge distribution and then derive this charge distribution over time. And this over time will give you the ID. But it is still like a partial derivative. We have not yet talked about what is the value of ID. It is still related to, okay, so there's a dx and it is partial ID again. So what happened here is that we want to get rid of the dv and the dx. Sorry, I think I missed the x here because we get the mu1 e, which is over the x. Here's the dvx over the x here. So I have so we have dvx dx here. Okay. So that will be still partial derivative form. So I want to derive what is the final ID we accumulating along the entire drain to source. And you can consider what is the current property, what is the principle of current property. If there's one none, there's no additional connection, the current flowing will equal to the current flow, right? That's what we mentioned in the electric circuit. And then what happened here is you can consider it is the blank box. And as soon as blank box, there will be no, the magnetic area will only along the surface of the semiconductor. So there, and the outside is perfect insulator. Let us first assume there's an ideal case. So after this ideal case, there will be no current flow out from this channel. So all of the current along the channel are exactly the same, right? So you can see this what we get is that we get the Vx dt of equals to ID. So if you want to get rid of this partition or the first order derivative, you just integral on both sides. So you take the dx to the other side, and we both have the dvx on one side, dx on the other side. So we take the both side integral form. Okay. So what happened here is that okay, so we can move the I to the other side. So the ID dx equals to mu n c r sine w vgs minus vx minus vt multiplied with the x. Okay, so you take the integral from both sides. And what is the boundary? How do we integrate? It is simple. From 0 to x. What is x? X means the channel length, right? So we integrate it from 0 to L, 0 to L. And then here it is the distance, or it is voltage. So if you integrate the voltage, it is voltage from 0 to equal at voltage at L. Okay. So the left side is simple. So it is linear. So ID multiplied with L equals to the potential integration dn outside W. Okay. So there will be only one factor which is x dependent, right? Only this one is x dependent. The other two seems to be just a regular product VGS minus VT. So you get a VL. So what is VL? VL means VDS. So how much different voltage we apply from drain to source. So this one we get a VDS. But here is we get a relationship between x, which is the first order. So when you take the Vx, it will be V squared over 2. You take the integral. And V squared over 2, take the boundary condition in, we get a VDS squared. So that will give you a negative side. Maybe I have a large bracket here. VDS over 2. Something like this. Okay, so that you can double check the unit because we get the square, we get a voltage square here. So we get the same unit to pass sum over to each other. And what we get is eventually we want to tell how much ID. Okay, so you get the L to the other side, U N C R side. W, here's W over L. For the errors is VGS minus VT, VDS minus VDS over 2 squared. Okay, so that's what we need. If you come up with the capacitance and come up with this relationship, we can say the ID, if you apply the voltage along gate and then draw the current from drain to source, you get this relationship. The current flowing along the channel equals to the mu(n), the mobility of the electron. It should be proportional to the current. That's simple. The higher mobility we get, the higher current we take. And over CR side, that will be interesting. If you have a larger CR side, you get larger current flow. Okay, and also W over L. So what is WLL? W is the width of this metal. So it's simple. If you get a large area, you get a larger channel. More channel you have, the larger larger current we draw. Okay, so that's simple. L divided by L. Why we divide it by L? If you get a shorter channel length, of course you get more current. Okay, and the multiplied with the resistance VGS VT, depending on how much accumulation charge along channel. Multiplied with VDS, just like the terms we have here. This one. Okay, but it will be additional minus 1 over 2 VDS squared. Okay, so you can consider if your VDS is really small in comparing with VGS minus VT. For instance, if your drain voltage is just like a 1 volt, your VGS minus VT can be 5 volt. Maybe you can get rid of the second because it will be relatively small in comparing with the first linear relationship. But if your VDS is large enough, you get certain saturation behavior. Okay, so these saturation behaviors will think of your channel and give you a negative sign to reduce the total current available. Okay, any questions so far? I think this one is really important and definitely will appear in your homework and finding. So please I think this one is really, really important. So please remember. Okay. And how about the other part? If you want to get a really high VDS, what happened here is that okay. So I try to start define what is the operation code. Before we get before we get a situation, so what does this mean? So we get situation means that the VDS is too high, so it pinch off the channel. It will impact the channel. Next, you get the trial region and the saturation region. The trial region, initially, it is linearly predisposed with the VGS minus VT and the VDS. But later on, it will be doing the trial region. So for instance, in trial region, VDS is much smaller than VGS minus VT. So the equation of the IB, the drain current equals to the equation we derived here. Okay, exactly the same. But in the saturation region, if you get a saturation region, what happening is that the drain source voltage is much higher than VGS minus VT. So for instance, VGS minus VT is only 0.1, 0.2 volt, but here is maybe 3 volt. So if you get a large contribution on the second part, what happens here is that you can replace like the VDS here. So VDS is much large, so you can just place the VGS minus VT into the VDS term. So you pinch off the channel, how much channel is limited by VGS minus VT. So once you place the VGS into the term, what you get here is, okay, so the highest VGS you can available is VGS minus VT. So put it into individual VDS, you get a simple IB equals to 1 over 2 W over 2 C V1 C outside VGS minus VT squared. So you can think that once the VGS is stationary, that means how much channel how much multi-carrier we can attract along the surface of semiconductor. It is the upper limit of your drain current. Okay, no matter how much drain voltage we further push up. So you can consider that if you draw the curve, not what we call the saturation region, we get a picture of the condition. The saturation regions will independent to the VDS. Okay, and this VGS minus VT determine how much saturation current we can get. So for instance, if you get a VGS much higher than the VT, so for instance, you get a VT plus 0.5 as the VGS, that will be lower than what we get from VT plus 1 as VGS. Okay. So this curve, do you remember what it appeared? Just like the BJT. Okay, what we have for BJT? We get like an emitter to collector curve. So we drain the collector curve from the emitter side. And then what do we get for the potential voltage? We get the BE as forward biasing, and how much forward biasing determines by how much IS is 100 VE over VT, right? That's how much IC we can get. Okay, and the collector voltage is not really important because if you follow with DC, we get exactly the same collect current because the collect current is limited by IC standard VD over P. Okay, so similar curve appear here. You get the saturation behavior even if we use higher drain or collector voltage. But one thing I need to emphasize several times, I think I emphasized that in the BJT course. What is the terminology for the saturation over trial region? So remind you in BJT, what we call it here is that in this region in which we get the same IC curve, we call it active region, right? And before it, we get saturation region in which we both forwarding on both sides. But in the MOSFET region, we call it saturation region when the current is clamped up because the channel is clamped. And then for the trial regions, we just linearly increase with the biasing voltage. That is because we get a different operation mechanism. Yeah, because we saturate the channel, but actually we do not have the channel in BJT. So we can say in BJT, we have the active, because for BJT, we work in analog circuit, we want to amplify the analog signal. So in that region, so we typically saturate the collection current. And this corrected current is determined by how much VB we can apply. And before that, we get the saturation behavior because at both junction we get the full values, so we get the saturation curve. Okay. So please remember, it is really important when you draw the curve. Please notice what is the region we are working on. In VJT, we work in the saturation region and then later in active region. But in MOSFET, we work in trial region and then later in saturation region. There will be two different cases. Okay. So okay. So for some maybe later. So for some simplification, typically you can rewrite the equations with the simplified model, or some people working this text in a textbook. So typically you can say we get the least one, the W over L is the scaling factor. So you can say how large your metal at the gate position. So get this as the aspect ratio. That means you get the scaling of this distance over the channel length, the width over the channel length. And the other one is that you can rewrite this UN DRI as KN not. So this one, it is in most of the case, if you purchase the MOSFET transistor, or you doing homework or midterm, sometimes they will say if the Kn pounds equals to 1. Okay, so that means you get a mu CR side. Okay. So I think there will be some quick example, but I think that's boring. So you can think that, for instance, if you are working with here's the example. If you think R size is 8 nanometer, and that your mu equals to 450 centimeters square Vs, your Vt is typically 0.7 volt. L median, what is the channel length? It's 0.4 micrometer. Find the CR side and the Km prime. So why we always say is minimum channel length, because you can always change the channel length. But the minimum one means that what is your technology node, as we thought before. If you have minimum critical dimension you can have based on your lithography is limited by 0.4. That is the shortest distance you can view between the source and drain. Okay, so typically you can change the channel length, but we prefer to use the shortest one to increase the current, and also we can shift the dimension of your entire bus. So based on this one, that will be simple, because if you already have the CR side, which is epsilon R side over T R side. So that will give you something like the 4.3 multiplied with 10 to minus 3 F meter squared. Okay. If you judge the K from, that is mu(n) the outside, which equals to 194 micro N all squared. And maybe a quick example is that you can conducting a current at 100 micro N. Is the driving the saturation. If you are working this current saturation, then the W over L is 10. What is this WL? Depending on what is your minimum channel length. So for instance, if you are working with 10, That means your crypto dimension of the length could be 4 micrometer over zero point 0.4. That is the minimal one. But sometimes you want to avoid any charge implication, like you have a certain variation. So people also maybe enlarge your dimension to 8.8. Okay, so you can try to play with downtown garbage in a verification inside. And other than the constants, you can play with this. So you can put every thing. And we assume it is saturation region. So that will be 1 over k from W over L VGS minus VT squared. Okay, so it is the equation in saturation region. And if you want to say it is 100 micro, it should be 100 micro N, right? Trying to find where I write it. Okay, so it is micro N, not the nail N, micro N. Okay. So if you put everything here, you get a VGS equals to 1 volt. Okay, so that means what is your VDS? VDS equals to VGS minus VT, so this should be 0.32 volt. So it's just like some quick example. So if you want to conduct the current at a certain level, get the design of a WL, which is the facultative part. And then how do you internally control the voltage? If you want to externally control the voltage, how much voltage do we need? What is the VGS minus VT? And then as long as your VDS is larger than its current, you can work in saturation region. So you get the VGS at least needs to be 0.32 volt along the sorry. Yeah, so at least you need to conduct the current, the voltage VGS at 1 volt. Yeah. And then the minimum VDS is 0.32 in order to simplify this equation. If your VDS is less than 0.32, what will happen? You are working in trial region. So there will be a lower current available. So you need to overpace this stage 9. So that means your VDS should be larger than 0.32. If you work with the VDS is slightly going to the stage 9, that means you work in trial region. You need to further get a lower current. So the current will go down instead of follow this equation. Any questions so far? Okay, so for some advanced technology, maybe I want to share some information for you. Do you heard about high-K material? Do you heard about high-K material in CMOS technology? Why we want to use high-K? Like, so a few things. First, how do we increase the current if your dimension is already limited by the lithography? For instance, we call it like a millimeter, and we cannot do further down if the process is limited by 20 millimeters, not only by lithography, but by different technology. I will talk about some, how do we replicate the LK instead 10 millimeter lithography. It's not possible to realize by the current lithography. So even with UV, what is the minimum dimension we typically can take for UV? It's typically, I think, around 9 millimeters. Okay, so it is not a really fancy, right? 90 millimeter. If you consider the channel length, it's already down far away. We talk about 2016. How do we do that? And how do we use the double taken mental function, but we talk about the limitation later. But you can think as technology further shift down, you will meet the limitation. What is the limitation? Source drain is too close. So we cannot shift it further. So we want to increase the current, but we cannot, but we can play with. Okay. So let us think about the situation current when you have the saturated current here? Or it is? Maybe like just go. I think that maybe this one can go back to the slide. One function we can play with. Okay, this one. So you consider saturated current. What is the parameter we take? W over L is limited, right? Because if you increase the current, of course you can increase the W. But what happened here? You increase W, increase the length of this device. That means you make it bigger. But we want a tiny device, but I want to shrink the device. We want both, not only have a mid-max device, but also have the higher performance. We need to double both as a new generation. Okay, so if you just double the current, but the device are bigger, it's in that. So sometimes people will prefer to say bigger or better. You have some definition like the VLSI. I'm not sure how many people take the VLSI before. If you want to design your current in VLSI, they will grade your scope, give you credit based on how fast you can operate a circuit multiplied with how much area, divided by how much area you need. So you get a higher score based on that. They will give you, like the peer will give you a table. If your score is within this scale, how much credit you will get. And that's really solid. You cannot find in my office. Please see this table. Okay, so that will be interesting. And that's the reason I didn't work in design, because when I really work 24 hours a day to find a main optimizing design, I still not in top 10, top 15, not in top 1. So waste a lot of my time there. I'm actually surprised why people can work really fast circuit than mine. So that we already have the optimized solution. Anyway, so the idea is it doesn't work. Okay, VGS minus V. We operate this? Of course not, because you get the power. You cannot say, okay, please use a higher battery for your circuit. For this top computer, do not use 5 volt. I want to use 10 volt, 15 volt. It's not possible. It's like a standard. We cannot change the logic voltage. Okay, it's not changeable. New one. Okay, so how do we change new one? What is new one? Mobility of silicon. Would you change it? Maybe slightly. We can use strain or stress to slightly change the mobility. Maybe not be on the open. So it's typically not a good way. And also, you can replace with your device like some people working in chip and field. That is power because you get higher mobility. But why it's not working yet? The chip is so expensive, right? The chip is expensive and then there's no good insulator. You get a lot of leakage. Okay, so what is the problem there? CR side, what is CR side? Let's take a look. CR side. Going next. This one. Okay, here. CR side equals to epsilon R side over PR side. Oh, since we have multiplied this because it is the thickness of your R side layer, right? So if you want to increase the current, how do we do? We want to reduce the epsilon. Maybe if you are working with outside layers, it is a physical property, you cannot change it, right? So you shift the dimension of the thickness. So that's the reason you can see why we want to use the risk thin layer. If you go back to the metal oxide semiconductor connection in the previous week, we talked about the thickness of oxide. If you reduce it, you can increase the capacitance. You can increase the current. We want to increase the current because if you have higher current, you charge up and deplete the current, deplete the MOSFET quick. So you get a higher performance of your transistor. That is the power. But then if you further shrink it down even already to 8 nanometer, what happens? You get leakage. You get some leakage in between the metal to semiconductor oxide to destroy all of these devices. All of this is built up. We have a perfect insulator. There's no leaky current, right? And then we can turn on turn off the channel by applying EGS. But if you get a different thickness thinner down to get a better current, that will destroy your device. So I think you heard about like Intel is the first foundry to derive the high-K material. I think it should be. It's hard for me to remember. Maybe 45 nanometer technology. You can check online. So I think people talk about high-K material like 15 to 20 years ago. They say that okay. So in CMOS technology, we use high-K in the block because we want to alleviate the loading of the CR side. We want to big, but I want to keep it still like thin enough to prevent the leakage. Okay. So why we use high K? Because if you consider the outside, high K material means the external is larger than outside. So typically 2 to 3 times larger. You just replace high K without changing any lithography, any dimension. You just boost up the curve by 2 times or even 3 times, 3 generations. That means you can play with this material for 1 and then take your bonus for 3 years, right? Without the changing lithography, without changing pattern. That's the power of material. People why we want to work with material. As long as we change the fabrication process, only single deposition. We just use insulator to replace the outside. We can get a better boost up in the current. Once you get a boost up, you get some benefit because if you get a higher current, you can shift the dimension. Okay, if you boost the current by 3 times, I can shift the dimension by maybe half. I still get the 1.5 times current, but I get a additional generation in shifting dimension, in shifting density. Okay, so that is the power. But you need to consider why people didn't consider high-K before, because you need to have a really good material. It's the work still as a perfect insulator, and also in the previous one, we want to avoid any trap density in between the surface, right? So I think it is a top secret back to 10 years ago. People did not allow you work in the foundry to know all the recipe of high-K because they are multi-layered, like the alpha outside, zirconia outside. So I think there will be a lot of combination. What is the simplest? Okay. So not only a single layer, it's single right now, right? A single outside layer, a single high-K layer. But like in TSMC, they get a 4 to 5 combination, like on the outside, alpha outside, in order to realize this. Okay, there will be multi-layer, and there will be a lot of different thinkings. Like this will be 2, 1, 4 nanometer as a combination. And how do we combine with different layers? And even you can do it with a perfect simulation in your model. How to do it with a good basic presentation. So if you get a different metal oxide data on surface, there will be some adhesion issue, there will be some defect issue. So how to deal with that one. So what I find here is you can strongly increase epsilon and keep the T outside the same without any leakage current on the metal oxide. Okay, so that is what we call with the metal high-K material. Okay. And then we will later talk about low K material. Why people want to use low K material? Definitely not a lonely layer, but they want to increase the frequency response. I think it is a really novel one in high K, maybe 24, I think. And then the next generation will be FinFET, the 3-dimensional schemes. And then later comes the gate-all-around system, I think in 2 nanometer, maybe. Yeah. And then let us consider the Venn diagram. I think Venn diagram is always important. So the Venn diagrams, we try to rotate the structures as the gate on top of the base, and we have the soldier beside. So here is the width, the dimension of the channel, and then it is the channel length. So hope you can understand how to change the drops. And then later on, we draw the Venn diagram. So what is the Venn diagram? We have the N, T, N. Okay, so maybe they draw it really fancy in a 3-dimensional case, but I want to just draw it in 2-dimensional case. It's because my poor drawing in a blackboard, so forget about it. Forgive that I can ask you in three dimensions. So if you consider here is the N-type, P-type, N-type structure. And how do we draw it is that, of course, we draw Fermi level first because we know Fermi level is always flat, right? And then here is the N-type. So what is the N-type semiconductor? That means your Fermi level proportion to conduction band. So get the same material, that means you get the same band 1.1 electron volt. And then in P-type system, there will be a depletion region. So it is in P-type region. And then later on, you will go to N-type one. And how much difference level? It could be symmetrical. But if you have different doping, maybe it's not symmetrical, depending on how much doping you have. So it is like a valence band. Here is the conduction band. Here is the Fermi level. And then here's the band. That is simple. And then since it is like a topic material, you can extend it further into the bulk material. So you can see that it is three-dimensional case that we have the Fermi level, we have a conduction, and then it will draw additional intrinsic level. So intrinsic level is almost the same in the middle of the conduction band and in the middle of the band diagonal. Okay, because we get almost the same NC and NV density, the density in conduction band, valence band, and conduction band. Okay. And then what happened here is that when you trying to apply, if there is no voltage on both drain and gate, of course, it is what we draw here. And if you have the gate voltage first, so what does this mean? You have a three-dimensional case. Unfortunately, I'm not sure how to draw it correctly. I will try. So in three-dimensional case, you can see here is metal. So here is metal. Here is oxide. Here is semiconductor. And then we want to draw the vertical line along metal oxide semiconductor. And as I mentioned, metal oxide semiconductor is simple because we just assume it already flat band. It is terminal. And then we tune the voltage. So we start to apply VG, which is started at 0. And then here is the P-type semiconductor. That means your Fermi level is a pro conduction. So that's why we apply it. It is not good because we want to have a some accumulation. Okay, if you forget this, you can go back to the previous lecture. Okay, so what happened here is the Fermi level is the same. And then since we apply positive voltage, we get a certain trap of electron here. And then here is the intrinsic level, the I. The Fermi level here is the P-type semiconductor, so first it is below the intrinsic level. But the later on, since we apply the gate voltage higher, so what is the total? We assume initially it is flat band. So what is the surface potential? 258. So what is 5 here? So here is 258. Okay, that is what we learned the previous one. Okay, simple, right? So you can connect this one together with this one. So initially it is P-type. P-type means that you work first this way. So first we work on this. But later on, since we apply the voltage, this one will be bent down. The entire three lane will be bent down. That means I don't want to draw it. You just look at this. Bend down this, right? So when you bend down this, you will identify what happens to the Fermi level. It will go up, right? It will go up to the intrinsic level. So when you bend everything down, you can see originally the EI, the intrinsic layer, is above the Fermi level, but along the surface, we bend it down. So you can see the Fermi level is above the intrinsic level. So you can see the bend down behavior. Not easy to do. Okay? And then later on, so we get it more complicated. We get the source string. The source is grounded. So we take the higher voltage along the drain side. when you apply the drain voltage, what will happen? So maybe we get rid of the accumulation layer first. We consider from this part. If you get a high voltage from here, it is N-type, here's the P-type. That means we get a reverse bias, right? If you do not consider get voltage here, there's the reverse bias. So if you consider reverse bias, what happens? Get a quasi-Fermi level. You split it. You split the Fermi level, and then you get the Fermi level for the down with the larger percent. So what happens here is that you get this one further down, get this one further down, right? And there will be a quasi-Fermi level along here. I'm not sure how to precisely call it. Anyway, so you can look at the so you get a quasi-Fermi level here, and then it's still like in reverse part. So in this reverse part, you get a depletion region. And then when you are working with depleted part, you get a mild carrier even least, right? Because there is a depletion region, you get a depletion region wider, and then you still have the same doping here. So this one will, if you do not see the potential along the gate one, you can see the behind, the one behind. You can see it will bend down a lot for both intrinsic level, intrinsic level, conduction band, valence band, and also you can see the Fermi level will be the quasi-Fermi level. Okay, so you get it go down. But along the surface here, you can see there will be additional potential. So not only the bend down, it will bend also down the surface of the semiconductor. So we can see that most the Fermi the conduction band bands along the surface of semiconductor and along the drain side will both peel down. Okay, so that will be interesting to see all of the. So you can see the depletion region is increased, and we have the Fermi level separate with each other. We have an EFN, and an EFP. And the EFN will go down because we say it is the multi-carrier. Okay, so for multi-carriers it go down, and we split the multi-carrier away. And then it will continue goes to the original part of the N-type semiconductor. Okay, so for N-type semiconductor, we still have the Fermi level on top of the intrinsic level. So that is what we have. So this one, EFN. Okay, so EFN and the EFNP, the quasi-Fermi level will later on combine the bucket material after the depletion region. So here we just introduced the intrinsic layer. So the quasi-Fermi level will be split here because you split the multi-carrier, so the multi-carrier will further go down instead of staying along this state. But the Fermi level, the majority carrier will be still the same, and they go here. Okay, so if you are confused, please go back to the regular PN junction with the reverse bias. And for the reverse bias, you can see the largest split of the Fermi level, and you get a large boundary in between the potential. Okay, but this one we combine together with this condition, so we also bend the house function down. So these potentials will be constant. So this will go down and this will go down. So the slope around this one will be mitigated instead of like there will be the accumulation, strong accumulation here. But since we depleted, you get these depletions without the N-type level. So you can think that along this path, we still deplete part of the multi-carrier away. So that means you get a picture of your Venn diagram. Okay. So we take 10 minutes break.